Hello everybody, how's everybody doing? Hope you're doing fine. First I want to mention again, so I will for the next couple weeks, that we have a conference in Lusaka, Zambia. All those who want to participate, they have a chance to buy their ticket starting today. So get your suitcases ready if you want to see an exotic land, okay? And if you have the chance. And I wanted to mention that the other day, I inaugurated my new site, website, known as ropehypothesis.com. And I put up a book, PDF format, that you can download. Some people had trouble with that. I guess that's to some degree been fixed as far as I'm concerned. There was a couple people who provided feedback, and I wanted to put you up to put you up to date on that. And this is the site, okay? And if you go up there where it says books, you'll find a book, okay? You can download it. It's known as the Rope Hypothesis. Tells you how to download it. Okay, just click on the link that's on that page. Okay, we modified the page a little bit today, but you should be able to find it. And get this thing here. Couple of the feedbacks that I got, one person said there was an error. And so we fixed that error today. So if you want to download the book up again, let me show you where the error is. Okay. And it was on this page. You will see that on that page, it'll say it's page 19. And we got the short links confused with the long links. Okay, so if you look at the long links up on the top, that's how it was. Now the new one says exactly in reverse. What confused us, and the reason we didn't pick up on this, is that you can see the waves coming out of the prism, okay? They have longer waves than the ones inside the prism. That is totally an error on the part of the mainstream. That's a bad way to illustrate it. And we saw that, and it just escaped our mind. It misled us to believe that, for a second there, so we didn't catch it. Yeah, it's the other way around. When it goes from the prism to air, you're going from supposedly a denser medium to a lighter medium, and somehow, according to the establishment, light speeds up. Something accelerates light back to 300,000 kilometers per second. So if a prism is made out of glass is anywhere 1.45 to 1.5 refractive index. That means it travels approximately at 200,000 kilometers per second through the prism, and then it speeds up back to 300,000. How light does that? Well, you got to ask the mathematicians about that. Yeah, under the rope model, light always travels at the same speed between any two atoms, whether it's the prism, whether it's air, whether it's water, liquids, gases, solids, it doesn't matter. Always at the same speed. Throughout the entire universe, the speed of light is the same. Why? Because torsion is the same. Why? Because the speed of light is c, little c, 300,000 kilometers per second between any two atoms. It's a torsion, okay? And all we change is, and here I can illustrate that, all we change is, the number of links and the length of each link. And then when you have longer wavelengths, essentially long link lengths, you have fewer links. So that's the trade-off between frequency and wavelength, which we call, under the rope model, we call it link length. Anyways, we corrected then a couple other minor errors, but you'll see that in the new book. So you may need to download it again. Sorry about that, but these things do happen. This fella who pointed that out, his name is Gabor. He also proposed to translate the book to Hungarian. And I guess Gabor is like Zsa Gabor. Maybe it's a very common name in Hungary for all I know. Maybe it's like Smith Anyways, he's going to translate. He proposed translating to Hungarian, and I'm going to be translating to Spanish. In fact, I am already translating into Spanish. So we got two languages. Anybody else who has like a mother tongue, which is not English, and wants it to translate it, well, they can contact us at here at Tokakaka. That's me holding the rope there, by the way. Okay. Okay, so there it is. That's the picture essentially. And yeah, you can contact us at Tokakaka Hotmail and tell us that, if you want to translate the book. Okay. And we'll send you a file, and Word file, and you can translate it, send it back, and we'll give you credit for it, obviously. And we'll also put your name on the honor list. Okay. Another comment that was made, my good friend Monkey Mind, and he said the following. He said that, sorry, got the wrong one here. He said that it was a question of whether the thread unwinds from the rope when it's spinning and creates this magnetic field. And it's a good question. We never resolved that. That's at least to my satisfaction. I have not resolved it in my mind. There are possibilities. One is that the thread unwinds. He was suggesting only one thread unwinds, the other ones remain straight, which was my original notion. My son Hans came up with this notion of double threads, which I thought was a little more logical. I still cannot vouch for it. And I'm proposing even a third one, which is that maybe it's the valence thread, the one that's on the outside of like an atom, that maybe swings around like we showed in one of the pages there. What was it? Page 58. And so you have this, when you form a molecule between two atoms, and it's an ionic bond, one shell goes through the other. Okay, and so maybe there's a process similar to that going on with what we call the magnetic field. In other words, the lines of force. And so there are different possibilities. I think the main issue, like I told him in a letter, is the following. Okay, so let me point that out for those of you who want to tackle the problem. And it looks like this. We have to identify what those lines of force are. Okay, when you sprinkle iron filings over a magnet, they align in a certain way, and it's always the same way. In other words, you always see a similar pattern. You can see it there on your upper right. You can see it there on your upper left. Okay, those are the patterns you're going to see. And so the question is, the mathematicians say, well, those lines of force don't really exist. Even though Faraday said it clearly, he says, those are physical lines. But they've disregarded, and he had a lot of experience with magnets, observing and testing them and playing around with them. But they said, the official version today, mainstream version, is that those lines of force are only used for explanation or for trying to describe what's going on with magnets and with the magnetic fields, but they don't really exist. Well, we got a problem with that notion, because that means that if those lines of force are moving the iron filings on the one hand and also creating attraction, they had better be more than angels and spirits. They had better be real. The fact that we can't see them and touch them, that does not make them unreal. Okay, and this is the problem we have. So I think the bottom line with the threads is we don't really know exactly how they're created, whether they're separation between two atoms that are not touching or not merged. For example, the serpentine there that you see on the lower right, it's a serpentine. That means all those atoms are merged and they spin around, and that's what we are saying that is the magnetic field, the spinning around of the threads that come out of those mergers. And the issue is whether, you know, you have a situation like the crystal there, the crystal lattice that you see up there in the center, upper center, where you see that they're all connected like by bed springs. That's the way the establishment shows many of the crystal lattices. And they say, look, you know, all these atoms are connected as if they were connected by bed springs. In other words, they vibrate with respect to each other, and et cetera, et cetera. And the question is whether the atoms are merged shell to shell or whether they are separated by ropes. That's the issue. And if they're separated by ropes, then this notion that Monkey Mind raised, which is the top one, whether it's one thread or two threads that come out of the rope, that's one issue. And the other one is that, you know, maybe it's the electron shell, one of the threads out of the electron shell that's coming loose, even though they're merged. So there are different possibilities that people would have to analyze each one. My point, again, is that we have to explain those, lines of force. And the lines of force are what make up the magnetic field. And the lines of force, this so-called magnetic field, causes a force through, for example, a coil, a live coil, a solenoid. Okay, so it causes a force. And hopefully that force is not mediated by spirits again. Hopefully there is a physical object moving in that region. The fact that we can't see it or touch it ourselves doesn't mean that those lines of force are not real. And the other thing that you should keep in mind if you want to tackle the problem is what I'm showing you on the lower right there in green, all the green little balls, those atoms which are merged. When they swing, they could be staggered. The threads could be staggered. In fact, the first one would swing first before the second one, the third one, the fourth one down the line when the current starts flowing. And so they start spinning. And when they spin, they swing these threads around, and those threads would not be on the same plane. That's the point that I'm trying to make, okay? So they would be staggered, and so that's another factor that you might want to consider if you want to tackle this problem, want to figure out, you know, how the magnetic field is made by not angels, not lines of force, but threads, physical threads. Physical meaning not that you can touch or see it. Physical means that it has shape, okay? And again, the definitions here are crucial. Anyways, those things needed to be clarified. Let's get on now with the subject matter of today, and that's going to be Mr. Aquinas and his buddy Niels Bohr. And as you can know, they've been debating seriously, not against each other, but in favor of each other. One guy does it with particles, the other guy does it with angels, but the properties of particles of quantum today and the properties and attributes that angels had in the 13th century in the days of St. Thomas Aquinas, or better known now as St. Thomas Aquanum, okay, is that, you know, they had the same properties, the same attributes. They had the same superpowers, okay? So what's the issue? The issue is we need to know what physics is, because that's where it all starts, because these people are doing physics. St. Thomas was explaining motion and time. Specifically, he was applying Aristotle's notion of particles, of points and lines, and he extrapolated them to this notion of time. They were analyzing time, okay? And so you look up and you say, well, what is physics? And because these are issues of physics, so is quantum mechanics. Supposedly they claim to be doing physics, so we need to get to the bottom of this notion of what is physics. And here we have from the IOP, the Institute of Physics, and you know, this is one of the, and I made those letters bigger so we can read them, but what they show is, you know, that physics has something to do with making smartphones smarter, GPS possible, music portable, and an interconnected internet, okay? So they see it as something related to technology. They think that physics has something to do with technology. This is a notion lots of people have out there. They think physics is all about, you know, creating devices and making our lives more comfortable, you know. And we're challenging that notion, obviously. It's got nothing to do with it. Technology has nothing at all to do with physics. That's what we're going to argue here. Okay? And so we have to look up, what is the definition of physics? Okay? Let's start there. And here, this is what we find. We find these definitions. One is in the Wikipedia, the other one is dictionary.com. You can look it up for yourself. You'll find something similar in any dictionary that you look it up in. Physics is the natural science that studies. We just study, we gawk, we just sit down and absorb something, whether we understood it or not, we just study it. Matter, it's motion and behavior through space and time. Through space and time. So you can travel through time. Time travel, yeah. Time is this body of water you travel through. Okay, and the related entities of energy and force, whatever those are, because those are undefined as well. So none of those four words have ever been defined, and that's what they study. What is physics according to dictionary.com? Science that deals. They don't study, they just deal with it. With matter, energy, motion, and force. So almost the same thing. Okay, so we have these notions that these are the definitions for physics. Okay, gives us an idea that they don't really have a good handle on the definition to begin with. You would think after thousands of years. I mean, who was it? Aristotle, who invented the word physics, and that's where we got the word originally from him, or his Lyceum, because there were other people working at the Lyceum other than him. He just takes the credit today. Okay, and so they created this word physics, and Aristotle defined it like more or less like I define it. It's trying to understand mechanisms, explanation of how this universe works. That's not the definition of physics today. Today they study and they deal with what? Energy and force and who knows what else that has never been defined, has nothing to do with physics whatsoever. And so here's another notion, and this comes from a site known as study.com, which they teach physics and other things over the internet. It says physics, the study, another study. They study, They don't learn, they don't understand, they just study. Of matter and energy is an ancient and broad field of science. One thing that may come to mind when you think of physics is that the many scientific laws. We have laws. There's a legislature, Congress, you've got all these representatives and senators and so on, and I guess they vote for laws, who knows, which are statements describing, keyword, describe, phenomena that have been repeatedly tested and confirmed. Confirmed to whom? To the Catholic Church? Who is this confirmed to? Physicists perform and repeat experiments. I didn't know that. I thought technicians did that kind of work. Gophers, they go to the lab and they do experiments. I thought a physicist is the guy who uses his brain, not his hands. But I guess they have a different notion. Physicists perform and repeat experiments, to formulate these laws, and explain how our universe works. Notice that they go between describing and explaining. They started describing, they say, we're going to be describing, now they explain how. These laws are so thoroughly tested that they are accepted as truths. By whom? Who accepts this as truth? What is it? A group of people up there that decided for all of us that they're going to accept this as truth and shove it down your throat? Is this what it is? And they can be used to help us predict how other things will behave. So now they're into astrology as well. They do predictions. Physics explains, again, natural phenomena in the universe. Well, that's kind of funny that they would use the word explain, because as we showed the other day, here we have authority. Okay, here we have authority telling us, no, that they have no idea whatsoever how to explain. Those who are not shocked when they first come across quantum theory cannot possibly have understood it. Evolution didn't equip us to be able to visualize quantum mechanics. Evolution did this to us. So we have two gurus there, Niels Bohr and Neo Susskind from the University of Stanford. And then we have Richard Feynman, Nobel Prize. He says, I think I can safely say that nobody understands quantum mechanics. Do not keep asking yourself if you can possibly avoid it, but how can it be like that? Nobody knows how it can be like that. The more you see how strangely nature behaves, the harder it is to make a model that explains how even the simplest phenomena actually work. So theoretical physics has given up on that. So no, they don't have any explanation. Not one rational explanation. And like Feynman says, they've given up on that. They don't even seek to understand how this universe works anymore. Okay, so it's beyond what is known as physics. So physics has been essentially redefined. It's not like Aristotle originally defined it. Okay. And so what did they get out of all this? Well, here we have the Khan Academy, another popular site on the internet. Okay, they do physics classes online. Okay, it says physics is the study, again, study, that word study, of the basic principles that govern the physical world around us. We'll start by looking at motion itself. Then we'll learn about forces, momentum, energy, and other concepts which are irrelevant to physics in lots of different physical situations. To get the most out of physics, you'll need a solid understanding of algebra and a basic understanding of trigonometry. I need to learn algebra and trigonometry. I mean, math is a language, and are these people saying that it's the language of physics? And yeah, if you look it up, you'll find comments like, here's a couple. These are just standard things that people write. These were a couple of gurus wrote in Quora, pulled them out because this is what the notion that people have, right? There is no doubt that this is a student of, advanced student of so-called physics, studying quantum mechanics. He says, there is no doubt that the most important language of physics is math. I cannot imagine how can people describe the physical process in quantum world without math. Describe, maybe. Certainly not explain. And the question is physics about describing or about explaining? I mean, I describe a chair, 4 legs, a backrest, and two armrests, and or that, the lion ran at galloped or whatever, 40 kilometers per hour, and I just described that, and that's science. I measure with a clock, and I get a Nobel for it? That's science, that's physics. Just measurement, weighing someone on a scale and saying you weigh 100 pounds. That's science, that's physics. This is what these people are saying. They're saying it's a description. Mathematics is the primary tool used by physicists to construct models, make measurements, and make predictions. Again, that word prediction, they're into astrology or something. Physicists use algebra, calculus, differential equation, linear algebra, group theory, topology, and more to unveil the mechanisms that occur on subatomic scales, relativistic scales, and everyday scales. So here this fellow thinks that all these mathematical line items, branches of mathematics or whatever, somehow help them unveil mechanisms. What does math have to do with mechanisms? Mechanism is an explanation of how something functions. How does math help you in any way? I mean, if you know that, for example, you let go of a pen or ball or whatever, and you measure, and it's 9.8 meters per second squared acceleration towards the center of the earth. Does that give you any mechanism about gravity, how gravity actually does pull that pen or ball to the center of the earth? No, it doesn't. Imagine, let me give you a for instance here. You go to the conference, so-called physics conference, and you see Michio Kaku, one of the gurus of mathematical physics, or you see Brian Greene, right? And so here's Joey, he sees them, and he approaches Brian Greene and says, "Oh, Mr. Greene, would you please give me an autograph?" And so Brian Greene says, "Sure, Joey, here it is." He gives him an autograph. And Joey says, "By the way, could you explain to me how gravity works while we're at it?" And Brian says, you know, Joey, in order for you to understand how gravity works, you're going to have to go to the university and study Chinese. Huh? Study Chinese? What do you mean I have to study Chinese? Yeah, you're going to have to study Chinese because that's the language in which we explain or describe how the universe works. So Joey said, well, you know both languages, you know Chinese and English, so can't you translate it for me in English? He said, well, you see, Joey, it's not a one-to-one correspondence. You know, you can't translate Chinese into English word for word, literally. Well, can you give me a ballpark notion of how gravity works, maybe just a picture? So sure, I can do that. Well, you have this four-dimensional fishnet. It's unimaginable. Don't try to imagine it. It's also infinite. We try to put it beyond the mind of the humans, but that's a different story. But the point is, you put a bowling ball in this net, and it weighs it down, and everything falls in that. And that's gravity. It's the warpage of space-time. And Joey says, but time, you're warping time, but time is a concept. How can you warp time? Well, Joey, I told you, you need to study Chinese in order to understand what I'm telling you, how gravity works, because unless you know Chinese, you won't really understand it. And so on it goes, on and on. These people say you got to study a language called math. You got to be expert in math. And if you want to understand gravity, and you say, well, can't you translate it for me? Well, here's the translation. The four-dimensional fishnet that's warped, that's gravity. It's geometry of space-time. And you say, but that includes time. Time is a concept. You say, yeah, you got to go to the university and learn all this math stuff. You got to learn the language. Or you got to be conditioned, right, to the language. Is that what it is? So what is the language of mathematics? Well, mathematics is a language of adverbs, quantitative adverbs. Mathematics does not deal with objects, and it doesn't deal with verbs. It doesn't care about verbs such as running or swimming. That's no good in mathematics. You need to know how fast, how much time. You need to have numbers and units in order to use any of those verbs in mathematics. And that's an adverb. That's a qualifier of a verb. You're qualifying, you're modifying the verb. So mathematics is a language only, exclusively, of quantitative adverbs. In fact, it doesn't use adjectives, it doesn't use verbs, and it doesn't use objects at all. It has no use for any of that. You know, you bring a tree and the guy says, what am I going to do with tree? Well, can't you put it in an equation somewhere? No, I can't. I can put the mass of the tree, I can put the size, how fast the tree was brought, all that stuff I can put in an equation. I can't put the tree in there. I can't put running in there. I can't put the adjective green or the word big in there. I need a number. I need to put 10 meters or 5 pounds. I need to put a number in there, followed by units. Then I can use that stuff. And so the issue is they developed a language, a very exclusive language of quantitative adverbs. And here, let me give you for instance, because see, under rational science, under rational physics, if you're going to stick around, you're going to have to learn a new language. But the good part about this language is that it's going to empower you. I'm not kidding you. It's going to empower. You're going to have superpowers suddenly. You're going to have the mind of God, so to speak. You're going to read a paper of the advanced literature, of so-called scientific literature, or even blogs, where they bring it down to the layman, and you're going to be able to spot all the errors, one right after another. This is the idea. Okay, I can't go into great detail today, but I'll give you a good feel for what I'm saying here. Okay. See, these are adjectives in ordinary speech. Okay, we have infinite, infinitesimal, continuous, straight, perpendicular, and so on. Well, in rational science and rational physics, we divide these up. We say, look, adverbs qualify motion. and adjectives qualify objects. It's black or white, straightforward. We can't confuse them. We can't use adjectives to qualify verbs, and we can't use adverbs to qualify objects. Okay? So it's very important to determine when someone is talking, giving you a presentation in a conference or whatever, or even if you read their paper or whatever, to distinguish and figure out exactly what is he saying, what is an object in his sentence, and what is a verb. Okay? I'm going to get to that in a second. I'll give you some examples. And you can see the word parallel there on the bottom. You say, well, why is parallel there under adverbs? Isn't parallel like, two lines kind of like the equal sign, right? And here, let me give you an idea of what's wrong with this word parallel. See, the way it's defined today in geometry, it's lines that do not meet. And they have this second corollary, so to speak, equidistant, like saying they're the same thing. And they're not. These two are two different kinds of definition. One is a verb. I like my verbs green, so I painted anything that's verb. I put in green so that people can spot it immediately and say, oh, he's talking about verbs. And I put my nouns in brown. Now, if you don't like it, maybe you're racist or whatever, well, you can change the colors any way you want, no problem. But the point here is lines that do not meet. Meet is a verb. And so this is the dynamic definition of parallel lines. It's not the same of equidistant, which just means that, these lines maintain a single distance, okay? And they involve objects. A line is an object. It's that two-dimensional plane that you see there in brown, and all we're looking at is the distance and making sure that the spacing between them, we don't care, we don't measure, we just say, the spacing has to be exactly the same between the two lines, and that's equidistant. So it's a photograph, it's a still image. Whereas the parallel lines that do not meet, how do you know they do not meet? That first of all, that's motion. But then how do you know they do not meet at infinity? I mean, maybe if you go another mile, they meet. So how long are we going to take these lines that are used by mathematical physicists and geometers, and they say, lines that do not meet. Well, do not meet where? I mean, a line is not really a line because they say it extends until infinity, and what, are you going to go all the way to infinity to find out if they meet or not? This is a proof. This is an operational definition, which is totally unscientific. And so, we put it under adverbs, their definition, because lines that do not meet is a qualifier. What they're saying is a qualifier of verbs. What they're trying to tell you is that, you got to perform some kind of experiment, and there's motion involved. It's a dynamic definition. And so you can't accept that in geometry because, again, what we're saying is parallel lines have to be, it's a static concept. You don't have to do anything. And these people are saying, you got to go all the way to infinity and find out if they meet. And so these are the notions that we're going to be showing, that there's a difference between what you find in mathematical physics and what we propose as an alternative in rational physics. And here's a list of other famous nouns which are really verbs. Orbit, orbital, infinity, motion, movement, change, itinerary, trajectory. All these are verbs as far as physics is concerned. These people treat them as nouns. And more than, they really reify them, and they come into being. Take for example the orbital. The orbital is many orbits of an electron bead around the atom, and so they say, well, the region where you can find the electron bead rolling around or wherever it jumps or whatever, we're going to cover that whole region. We're going to call that an orbital. That's where they got the word. The word orbital essentially comes from orbit. So they've turned many hula hoops into this ball, which they call an orbital. And then it's a vague notion even in that sense. But all these words are verbs. And so you don't treat them as nouns, okay? And so this causes a lot of problems. And until you can master the language of rational physics, you're going to have trouble. So as homework, maybe you should consider reading a blog or a paper. It could be even from a what is it, one of these sites that popularizes physics, space.com or one of those, or Astronomy Magazine, and you'll find articles which are readable, which are not so technical in their language, and you're going to spot the errors immediately. If you use this criterion, you're going to go in there and say, okay, which in this sentence, what is the noun? What is the verb? Does that noun include motion within it? Does it embody motion? And so on down the line. And then you're going to say, well, how do they qualify? They use an adjective to qualify a verb. They use an adverb to qualify what is truly a noun, an object, and so on. You're going to be able to spot that. Suddenly you're going to be able to see much more of the world than what you've read so far. You really got to put your mind into using this new method of analyzing, what's out there. Here are others. These are static nouns. Okay, let me put it over here. Again, these are not nouns. Okay, for the purposes of physics, universe is not a noun. Okay, we can't talk about the universe. Okay, it's a concept. It's a relation between space and matter. It includes both words. It's a someone establishes a relation by using that word by the definition itself. Space, vacuum, ether. What's ether? Many particles. That's what it is. Location, position. All these words are concepts. You can't use them as objects. Point, line. We discussed that a couple sessions ago. Point is, if you're referring to the dot, that's a physical object. And if you're referring to what it represents, the location, then you're talking about a concept. And so you can't use them both in one. You got to decide, is the word point refers to the dot, or does it refer to location? You can't have it both ways. God cannot be both an object and a concept. That's the question. That's the issue. And what is this language for? What do they use these terms for? Well, let me give you, for instance, here you'll see, you might come across an inclined plane, okay? And they say, okay, I understand that. It's a ball rolling down an inclined plane. Very simple, right? But this is no use in mathematics. So what they do is they say, no, look, it's not, what you have is mass rolling down, okay? It's mass that is rolling down. And you say, well, why is it going down? Well, it's going down because it's being pushed by force. And you have time transpiring. In other words, you got a clock that's rolling. And what it all creates is this energy, right? That is some kind of spirit that comes in and fills the equations. And so this is the way it's explained. This is the mathematical language. The language of physics is here. That's the language of physics, okay? So you're going to have a difference between how a mathematician talks and how a rational individual talks, especially rational physics. And you need to look at especially, which ones are the nouns, which ones are the verbs, and these people are just moving concepts, and they're qualifying them with the wrong qualifier. Whether, if they're going to be moving mass, they can't say green mass. Okay, they're not going to use an adjective for that. Why? Because mass is not a physical object. So you can say the green ball rolled because you're applying an adjective to qualify the ball. That's standard. That's no problem there. But you can't use green to qualify the word mass or energy or any of those words. And for that, you need an adverb, which again shows you that the word they're using is not a noun. It's a concept, usually a verb that's been reified and converted into a noun. And that's the language of mathematics, which they claim is the language of physics. So you see where I'm going with all this. Anyways, we had the same problem with Mr. Aquinas, okay, Thomas Aquinas, Tommy. And what he did was he used this same type of language. Why? Because he used the words that he got from, wrong one, hold it. Let me get this other one here. The words he got from Aristotle. Okay, so those are the words I use. And here we have, what we were looking at in the past weeks. We have Mr. Aquinas on one side, and we have Mr. Bohr on the other. And we dealt with the first few issues there where Thomas was analyzing how angels behaved and what properties they had, and they match exactly the ones that quantum mechanics has assigned to their particles. The last two are the ones we still have not covered, and the first one is whether an angel or a particle can pass through an intermediate space, and whether the movement of an angel or a particle, for that matter, is instantaneous. And so let's answer the first one by Mr. Tommy there, okay? Let me put myself back in here. If I can get myself in there. So he uses this notion. He says, let me get this other one first. Hold it. Give me a second here. So we put it in the right context. Some of these are sometimes difficult to get in there. He wants to answer whether an angel passes through the intermediate space. And for that, he's going to have to use the term, he's going to have to analyze the same word that Aristotle analyzed, which is the word continuous. Okay? And so he says the local motion of an angel can be continuous and non-continuous. Okay, so it could be one or the other. If it be continuous, the angel cannot pass from one extreme to another without passing through the mid-space, because, as is said by the philosopher, and that's he called Aristotle the philosopher, and he goes in and analyzes, some of the what Aristotle wrote in his book Physics. And this is the critical point, which Aristotle has in his book 5, which is the one mentioned by Thomas here. He says, points can touch while units can only be in succession. Moreover, there can always be something between points, for all lines are intermediate between points. What is he talking about? Well, when he says line here, he's talking about distance, but distance is represented with a line, and really he's talking about distance traveled, and so he's saying you can travel from point to point. That space he calls a line. Okay, whereas it is not necessary that there should possibly be anything between units. Huh? What is he talking about? For there can be nothing between the numbers 1 and 2. So you can see that we're talking about continuous, and what is continuous? Well, under rational science, under rational language, continuous is an adjective. It cannot be used to analyze what these folks are doing here. They should use the word incessant, because they're talking about motion. So they can talk about constant motion, incessant motion, but not about continuous motion. Continuous is an adjective and applies to tables. You can say a continuous table if it were made of a single piece. But when you talk about motion, you can't use the word continuous. Not in physics. In ordinary speech, yeah, but not in physics. In physics, continuous is an adjective, and you have to use an adverb. And an adverb is like incessant, and you can say, but incessant is an adjective in ordinary speech, not in rational science. In rational science, incessant can only be applied to verbs, to motion, to dynamic scenarios. So you would say incessant motion, continuous table. That's the way we use the language. You can't say incessant table. And likewise, you can't say continuous motion. And these people are using the word continuous to define, to apply it to, they're talking about time and motion, and then suddenly, out of nowhere, this guy says, Aristotle says, oh, by the way, the numbers, you got the 1 and the 2, and there's nothing in between them. How did we jump to numbers? It's like they're mixing all kinds of nonsense in there and giving you examples that out of nowhere that have nothing to do with the subject at hand. And this is what you're going to see not only with Aristotle and St. Thomas Aquinas, but you're going to see it with Bohr as well. And so here's the crucial part that St. Thomas was trying to say, okay? I think this is the bottom line on his analysis of that, and that's, while an angel is moved locally, his essence is applied to various places. That's how he solved it. He says, yeah, the angel can pass through intermediate space. Why? Because even though he's locally like circumscribed to a space of sorts, his essence, his soul, the soul of the angel, because the angel is soul, is applied, everywhere. So he gets the both worlds without justifying. He's just making this magical analysis and saying, see, yeah, an angel can pass through an intermediate space, just like he can be everywhere at once, like we discussed the other day. He can also pass through intermediate space because he's already there. He's already on the other side. And so how does quantum mechanics answer this? Well, we answered that the other day with John Rennie, the guy from who ran, what was it, Scientific American. And he says the photons do not have well-defined trajectory. The diagram shows them as if they were little balls traveling along a well-defined path. However, the photons are delocalized and don't have a specific position and direction of motion. So we're not talking about, photons like being particles. He's introducing magic here, just like St. Thomas is. The photon is basically a fuzzy sphere expanding away from the source and overlapping both slits. So here we have, this wave, the spherical wave that is instantaneous because, the wave function can collapse and turn into a point, and the point, or the dot, or the particle, or the corpuscle, or whatever they want to call it, suddenly can construct itself or demorph, and suddenly that thing covers the entire universe as a wave, because the wave has no endpoint. And so it's more or less like St. Thomas angel there, that is not only moved locally, but he can apply it to various places. And that's the magic of the wave. The wave can collapse to a particle, whatever a particle is, and then the particle can also turn into a wave at the tip of the magic wand of the magician, okay, or mathematician. So he says the photon is basically a fuzzy sphere expanding away from the source and overlapping both slits. That's why it goes through both slits. So if you want to know why the light goes through both slits, well, because it goes out as a photon, it then turns into a wave, it covers the whole room, and then it condenses back into a particle on the other side of the slits for whatever reasons. That's magic. That doesn't give us any insight whatsoever in how the slit experiment works. And he said the photon position is only well defined when we collapse its wave function. So they take a wave function, which is a concept, they collapse it, they turn it into a particle, which is another concept, because according to at least Sean Carroll, it's a excited field, which is a concept, right? So they play around with these words. And none of them are nouns. All of these are verbs or concepts of some kind, okay? Usually they're verbs. And then, so you can see why, there's no difference between St. Thomas's angels and quantum mechanics particles, so-called particles, whatever particles are, because they never define that word very well. And then there's the other issue. The remaining issue was whether an angel can move instantaneously. And this is what Aquinas has to say. He said the local movement of an angel is instantaneous, but that's the local movement, okay? They said that when an angel is moved from place to place during the whole of the preceding time, he is in the term where from. But in the last instant of such time, he is in the term where to. So it's from where and to where, okay, kind of thing. Nor is there any need for a medium between the terms, just as there is no medium between time and the limit of time. So there's no medium. That's how he's saying. So in a way, the angel, can move instantaneously because there's no medium between time one and time infinity or whatever. And just to cut across, we can go to that last line. It says, an angel can be in one place in one instant and in another place in the next instant without any time intervening. Okay? Now, doesn't that sound like quantum and a little bit like general relativity as well, right? And so what is the answer of quantum mechanics to that? I mean, do they have anything even similar to that? And yeah, of course, they've come up with the same notion, okay? And they've done it for particles and for essentially all of mathematical physics. And this is what they came up with. Heisenberg came up with the uncertainty principle. That means that you can't tell the position and the momentum of a particle simultaneously. The more you know about one, the less you know about the other. You've heard of Spock and the crew, Captain Kirk and so on. Teleportation, you've heard of that. It's instantaneous movement. You don't go in between. You're reassembled at destination. And tunneling, it leaves as a particle, goes as a wave, goes across the barrier, and then arrives as a particle on the other side. And so it's like, either you can interpret that two ways. Either the thing just went from one location to another without passing through the locations in between, or as Aquinas says, you can go from Spain to Syria, or I can think of going from Spain to Syria without passing through Italy. That's how Aquinas explains. And that's more or less what these people are saying. That's what tunneling is. You go from Spain to Syria and you don't have to go through Italy. Okay? The particle starts out, turns into a wave, stretches its neck across the finish line, and it's detected as a particle on the other side. And they say, oh yeah, the particle just made it through tunneling. What is tunneling? It means there is no time between starting and ending point. That's essentially what it is. They're getting rid of time. They're saying, somehow the particle is already there before, almost at the same time it left. And so there's no time in between, and they say, well, it's very simple. The wave stretches or occupies the whole universe, or was already there. And then when you're going to measure, it collapses into a particle instantaneously, always, right? And so there's no motion, there's no time. It's just instant. And so these people have all arrived at the same, today, quantum mechanics has arrived at the same conclusions that Mr. St. Thomas Aquinas arrived at almost 1,000 years ago. That's the status quo. And all this is related because the arguments that underlie St. Thomas Aquinas's arguments, the underlying arguments all come from Aristotle. He's the guy who came up with this notion, or at least he's the guy who wrote about it, because I think it came even 200, 300 years earlier, where they talked about particles, and they talked about points, and they talked about lines, and that's what they used to describe location, what they used to describe distance, and specifically distance traveled. Not distance as in separation, but in distance that you have to move through, displacement, okay? And that's what they use. They use the line for displacement. They use the dot to represent the point, the location. And they call this one a point, this one a line. And that's what they based all their analysis on. And St. Thomas Aquinas borrowed all that. He did an analysis on angels, showing how they can go from one place to another without going to intermediate spaces because they have all these superpowers. And quantum mechanics have picked up on that in the roaring 20s. And they say, oh, we can do the same thing. These particles just go from here to there without going through the intermediate space, and they can be at two places at once. And many can be at one place at the same time. And so on down the line, they have all these magical superpowers. Are those explanations? First of all, you need to understand the language. And if you understand the language and you understand that mathematical physics is, the underlying language is mathematics. And mathematics is only a language of quantitative adverbs. And they have trouble, qualifying nouns and verbs because they go back and forth. They use adjectives for verbs. They use adverbs for nouns. Then once you pick up on that language, then you can see real quickly when you read, something that's been translated from the official the technical magazines into layman's magazines, you're going to be able to read and say, hold it, is this guy talking? Is that a noun? Is an orbital a noun? Is motion a noun for the purposes of physics? Is an itinerary a noun? Once you look at all these things, you realize that what they've done is reified the language. They're using verbs as nouns, and then they're qualifying it with adverbs. And what they're actually doing is using an adverb to qualify a noun, an object that's been reified as a noun. That's what they're doing. And so you have all this mixture. The only way you're going to get to the bottom of that is identifying what really is a noun, what really is a verb, what's an adverb, and what's an adjective. And that's the language that mathematical physics has never yet mastered. All they use is quantitative adverbs. Anyways, we will continue with geometry next time around. And if you have, again, any issues with the book, if you find any more errors, so to speak, well, let me know. You can get it to tokakaka@hotmail.com, and we'll be glad to listen to you. Thank you, and we'll see you, on Sunday? We'll see you then. Bye-bye.